In the last lesson, we saw that the pressure difference across two mesh resistors in parallel was the same. We also saw that the total current entering a junction is the same as the current leaving the junction. Let's see if the same rules apply to an electrical circuit. We're talking about Kirchhoff's junction rule, which is based on the law of conservation of charge. When I say that charge is conserved, it means that the total amount of charge in the circuit stays the same. And when we talk about charge, we're also talking about current, because current is the rate of flow of charge. So it follows that if charge is conserved, current also must be conserved at each junction. To best demonstrate this, let's look and see if it's true with our electrical circuit. So we have a circuit with two resistors in parallel and one battery. Let's say we know that the total current leaving the battery is 5 amps. When the current reaches this junction, the current's going to split up, just like cars on the freeway. If 5 cars enter a junction and 2 cars go one way, 3 cars have to go the other way. Cars don't appear out of nowhere and they don't disappear. So it's the same thing with our circuit. If 2 amps goes down the first branch, then 3 amps must go down the second branch. This way, the total amount of current remains 5 amps. Now we'll look at an electrical circuit with 2 resistors in parallel and see if the current remains the same. So first I'm going to measure the current leaving the battery. I get 72.7 milliamps. Now I'll measure the current going into the second resistor. Okay, now I'm measuring the current going into the 305 ohm resistor. It's 19.84 milliamps. Now I'll measure the current going into the 105 ohm resistor. The current going into the 105 ohm resistor is 55.5 milliamps. So if we add the current going through both resistors, we get 75 milliamps. And we measured the current leaving the battery as 73 milliamps. So we have some extra resistance in the circuit because of these banana clips. So it's not going to be perfectly equal, but basically what we see is that the current leaving the battery, the current entering this particular junction here, is the same as the current leaving the junction. So our observations are consistent with Kirchhoff's junction rule. Now let's look at a circuit on the tablet. Let's look at a circuit with a 6-volt battery and 2 resistors in parallel. One of the resistors has a resistance of 105 ohms. The other resistor has a resistance of 305 ohms. We're going to follow the path of a charge around the circuit. Remember that conventional current is the direction that positive charge would flow. So first we need to calculate the current leaving the battery, and we can use Ohm's law to do that. First we need to find the total resistance in the circuit by combining our resistors in parallel. So it would be 1 over 105 ohms plus 1 over 305 ohms gives us a total resistance of 78.1 ohms. So that's the total resistance in the circuit. Using that total resistance, we can calculate the current leaving the battery using Ohm's law. So let's do that. So 6 volts divided by 78.1 ohms would give us 77 milliamps. As we've seen in previous lessons, potential difference is the same in parallel. So both resistors will have a potential difference of 6 volts across them. So using Ohm's law, we can find the current through each resistor. So it would be 6 volts divided by 105 ohms, and that would give us 57.1 milliamps. We'll do the same thing with the 305 ohm resistor. Using Ohm's law, we do 6 volts divided by 305 ohms, and that's 19.7 milliamps. Starting at point A and moving counterclockwise around the circuit, we'll go this way. We'll go first across the battery, from the negative to the positive side of the battery. So let's sum up the changes in potential when we go around the circuit. So when we go across the battery, that's a positive 6 volts, and we'll take the smaller of the 2 loops and go across the 105 ohm resistor. So let's find the potential difference across the 105 ohm resistor. It would be negative, and you would take the current multiplied by the resistance to get the potential difference across that particular resistor. So you end up with the total change in potential of 0 volts when you go around one complete loop of the circuit. You would get the same result if you went across the other resistor. Let's try that. So we'll still start at point A, and we'll go clockwise again, and we're going to add up the changes in potential. You gain 6 volts when you go across the battery, and then we're going to go down, all the way down here across the 305 ohm resistor. We're going to lose electric potential when we go across this resistor. You take the current multiplied by the resistance, and again, you get 0 volts. This is consistent with Kirchhoff's loop rule, which states that the sum of changes in potential around one loop must equal 0. Since electric potential is electric potential energy per unit charge, the change in potential is proportional to the change in electric potential energy. Since the sum of the change in electric potential is 0 around the circuit, that means the sum of the change in electric potential energy would also be 0. This is consistent with the law of conservation of energy. Let's check Kirchhoff's loop rule with our electrical circuit. All right, let's measure the potential difference across the components of the circuit. For the battery, I have 6.17 volts. For the 305 ohm resistor, 6.16 volts. And the 105 ohm resistor, 6.16 volts. So we can see that this is consistent with Kirchhoff's loop rule. There's a gain in 6.16 volts when you go across the battery, and then there's a loss of 6.16 volts when you go across either resistor. So the sum of changes in electric potential around our loop is 0, which also means that the sum of the changes in electric potential energy is also 0. So this is consistent with the law of conservation of energy, and it's consistent with Kirchhoff's loop rule. Now you'll use a simulation to answer some questions about circuit behavior.